Hello everyone, my name is Behzad Farahani, a researcher from Energy, Portugal. Today I'm going to give you a presentation on an overview on the stress dead zone concept to obtain the stress intensity factor in the VCSI 2020, the first virtual conference on structural integrity. The research team includes me, Professor Queiroz Melo, Dr. Paulo Tavares, and Dr. Pedro Moreiro from the Laboratory of Optics and Experimental Mechanics of Energy. So my talk includes introduction, model definition, and the experimental procedure, actually focusing on the polycarbonate middle tension specimen, in which 2D digital image coloration and the tensile test has been included. And basically the next stage is related to the analytical methodology based on the compliance formulations, and as a result SIF calculation is going to be presented based on the stress dead zone concept, digital image coloration, numerically by the finite element method, and a reference solution is going to be given by the ASTM standard, and afterwards the comparison and the conclusion of my work. Okay, so the first section is devoted to the introduction. Basically, the work that we have already conducted is related to the new analytical solution for the SIF calculation. So in order to prove the concept, it was needed to make some experimental and numerical test. So in order to do that, a middle tension specimen with a central notch, which is made of the polycarbonate optical grade, was submitted to a pure tensile condition in Unixion, and 2D digital image coloration was used in order to evaluate the experimental data and monitor the deformation field in order to calculate the stress intensity factor. Moreover, based on the standard ASTM, the specimen was prepared and the SIF was calculated as a reference solution, and the compliance method was employed in order to acquire another stress intensity factor based on the dead zone concept, that it is the main goal of this work. And computationally, the problem was resolved using the finite element method, and the obtained results were acquired in order to make a comparison between all the obtained results, and also the dead zone characteristic has been also surveyed. So the model definition, the middle tension polycarbonate specimen has been prepared based on the ASTM standard, and afterwards it was pre-cracked by 1 millimeter on the notch on both sides. The geometrical properties, as can be seen, is W 30 millimeter, the thickness is 3 millimeter, the radius of the hole is 1 millimeter, the initial notch AN is 6 millimeter, and the crack length is 7 millimeter. The material properties have been taken from the literature, Young's modulus, Poisson ratio, yield stress, and also ultimate tensile strength. As can be seen in the figure, the experimental test has been done by instrument machine with the capacity of 1 kilonewton. Two halogen lamps were positioned in front of the specimen. A camera has been positioned in front of the specimen, and the gripping system is showing in the right side. The maximum capacity of the machine has been used, so the applied load was considered as 1 kilonewton with the frequency of 10 hertz. In this slide, I'm going to give some description on the analytical methodology based on the stress dead zone concept. So on the right side, you can see an image which is showing the plate with the central notch, which is pre-cracked, and The region which is highlighted in red is demonstrated as the dead zone, which means that this is the minimum deformation variation during the tensile test or fatigue crack growth test can be negligible from the fracture calculation. So the literature at Anderson, as you can see on the bottom side, reported that this triangular region possesses approximately a height equal to beta by the crack length, where A presents the crack length and the beta is the 1.2. So the equation is going to be presented here. So just a quarter of the model is going to be considered. In this case, the P prime is the applied load divided by 2, and the small w is the total weight divided by 2, and A and uncracked ligament W minus A. It is possible to obtain the displacement field and afterwards the strain and stress field on the uncracked ligament. And finally, it is possible to obtain the vertical displacement by the integration of Vxy equal to P over 2EB integrated from 0 to beta A dy over W minus A plus Y over beta. This is the vertical displacement. In this slide, the stress intensity factor is going to be calculated by the concept of the dead-stress dead zone, and so the vertical displacement has been formulated in the previous slide. It is going to be used here in the integration and in the derivative in terms of the crack length, and according to the energy release rate, it is possible to formulate the stress intensity factor mode 1 as can be seen on the right side, the first equation. So if the following values of the crack length, beta, width of the plate, and also the plate thickness and the applied load considered, so the stress intensity factor in mode 1 can be calculated as 62.36. Stress intensity factor calculation using digital image correlation is presented in this slide. The full deformation field has been derived from digital image correlation analysis, and the data was processed by VIC2D software. In order to obtain the result, a window of 7 by 7 millimeter was selected exactly after the crack tip, and the strain has been monitored in this window. So the polar coordinate of the points locating in the window have been obtained according to the crack tip. By using the Williams series expansion, it was possible to extract the mode 1 stress intensity factor as can be seen in the formulation. So the stress intensity factor was calculated as 60. The problem was numerically solved in Abacus using finite element method formulation. On the right side, the finite element mesh is demonstrated, applied load, the boundary condition, the number of elements and nodes, the CPS4R elements has been used. So the crank was model relying on the contour integral models, and the SIF was calculated for the 10 contour integrals based on the maximum energy release rate criterion. So the mode 1 SIF was calculated as 61.39. And finally, the SIF calculation by ASTM, which is considered as a reference solution. Alpha is 2A over W, according to the ASTM, is 647 international, as can be seen in the bottom side. So the stress intensity factor was calculated as 60.42. In this slide, the comparison amongst the obtained results on the stress intensity factor is presented for ASTM, digital image correction, finite element method, and compliance function. the table is presented, also the deviation between the studies, and the small deviation less than 4% was verified. Moreover, it is possible to focus on the stress dead zone characteristic, as it was beta, and it by the literature it was reported as 1.2 by A. So the figure is showing this is the strain field. So the crack tip accounted for the maximum strain. I'm talking about the kidney shape. So both verified from digital image correlation and finite element method. And the triangular region is the dead zone with a height of 1.2A. So the strain field validated the characteristic of the dead zone both in shape and in quantity. The conclusion of this work can be stated as the actually the characteristic of the stress dead zone, and also the compliance function application on the stress intensity factor calculation in order to prove the concept of the stress dead zone. A middle tension specimen made of the polycarbonate was uniquely tested, and digital image correlation was used in order to analyze the experimental data. The model was also solved using finite element method formulation in order to obtain the comparable solution on the stress intensity factor and also deformation. And the encouraging results prove that the proposed analytical formulation, which is based on the compliance method, has been correctly implemented, and the stress intensity factor and the dead zone characteristic were verified, and the result obtained from digital image correlation and finite element method put into evidence that the supporting methodology is efficient, reliable to elastostatically study the pre-cracked plate, and in this case it was used for the polycarbonates. The presentation is over. I would like to thank you all for your attention. I acknowledge the project, Miami project from INEGI and also University of Porto. And if you have any questions or doubts, please let me know. Thank you.